Welcome to the Morning Walk with Murty Digital Stroll.
Glad to be here for this one. I think it's going to be a really, really fascinating walk today.
Yeah, absolutely. So today we're looking through what we call the digital prism to extract a very specific piece of legacy code.
Right.
Because, when lead architect Murty BVNS laid out the framework for Project Antaryami, the whole idea was to identify robust, decentralized systems. We're talking about those analog architectures that actually survive the test of time.
The ones that don't just, crash the second your Wi-Fi drops.
Exactly. We are hunting for solutions that are permanently resilient.
Which is really why we analyze history, not just as this simple timeline, but as a vast repository of abandoned technologies. Sometimes the most brilliant solutions, they aren't waiting in the future. They're actually buried in the past, completely forgotten, just because the economic models changed around them.
Yeah, and that actually leads perfectly into today's spark of inspiration. I was reading this incredible piece titled, Water Does Not Run Uphill. Every child learns this. Every engineer confirms it.
Yeah.
It was published by Nature Lost Vault. And it's just such a brilliant fellow traveler's spark for our conversation today. The way they framed the physics of water, it instantly clicked with what we're trying to uncover.
It really is a beautifully composed piece. It captures the sheer, stubborn reality of gravity and physics, which, sets the stage perfectly for this digital prism framing.
Yeah.
They somehow managed to turn a fundamental law of nature into this really compelling mystery.
They really did. So I want you to picture this paradox with us as we take our walk today. What if the ultimate piece of perpetual off-grid hardware was invented by, of all people, one of the world's most famous hot air balloon pioneers?
It's wild just thinking about it.
Right. And what if this invention was so groundbreaking that it was rapidly adopted by the greatest industrial empires on Earth, like installed in grand estates, used to irrigate vast frontiers?
And then it just vanishes.
Exactly. What if it was entirely forgotten? Not because it stopped working. It never stopped working. It was discarded simply because no one could figure out how to, charge a monthly subscription for it.
And that right there is the core tension we are unpacking in this Google session.
Yeah.
Because from an auditing perspective, you are looking at the ultimate decentralized hardware migration.
Yeah.
But philosophically, in the spirit of Google Cool 2.0, we really have to ask why humanity systematically discards sustainable knowledge.
Why do we trade our independence for convenience?
Exactly.
So let's start with the original programmer of this legacy code, because the problem he was trying to solve was intensely physical. We're traveling back to France, 1740, to meet Joseph-Michel Montgolfier.
Okay, 1740.
Yeah, he's the 12th child of a French papermaker, and his family famously described him as this, restless dreamer.
The guy who would just stare into the fire, right?
Totally. He was the kind of guy who would literally just stare into the hearth fire while everyone else in the house went to sleep.
Because he was just completely captivated by these unseen forces of energy.
Right.
So by 1782, he's sitting by the fire, watching the smoke curl up toward the ceiling, and he asks this massive paradigm-shifting question. He wonders if a bag could be fabricated large enough to, catch that rising thermal force, trap it, and actually carry a man into the sky.
Which he actually achieves. By June 4th, 1783, Joseph and his brother Etienne launched the very first hot air balloon.
A massive spectacle for the time.
Oh, absolutely huge. The balloon travels over a mile, reaching 3,000 feet in the air. All of Europe is transfixed.
Yeah.
But, from a systems architecture standpoint, this is where his story gets incredibly interesting to me. Montgolfier essentially gave humanity its very first cloud technology.
Literally in the clouds.
Literally. But his actual day job, the family business, that required serious on-premise infrastructure.
Because papermaking in the 18th century was incredibly resource-intensive, particularly when it came to water.
Oh, massively.
You need huge amounts of flowing water to power the mills, to pulp the wood, to process the sheets.
Right, and the family paper mill had a major logistical bug. The facility was up on a hill, but the river they desperately needed was stuck way down in the valley.
And you can't exactly run a paper mill in a hot air balloon.
No, exactly. You need physical tons of water moved up a steep incline every single day. So Montgolfier takes that same restless observational mind that conquered the sky, and he points it down at the river.
And the brilliant thing is, he didn't try to invent a new force of nature to move that water.
He didn't build a better water wheel.
No, he just observed a very common plumbing nuisance from a completely different angle. He started looking closely at what actually happens when flowing water is suddenly stopped.
Okay, like when you turn off a faucet really fast.
Exactly like that. Imagine water rushing through a pipe and a valve is suddenly slammed shut.
The water doesn't just politely stop, right? There is a massive amount of kinetic energy in that moving weight.
Right, that momentum has to go somewhere.
Yeah.
The kinetic energy instantly converts into this violent pressure spike that travels backward through the pipe, kind of like a shock wave.
Okay.
And every plumber in the world knew about this phenomenon. They called it a water hammer.
A water hammer.
Yeah, and to the rest of the world, a water hammer was this terrible bug in the system. I mean, it violently rattled pipes, it shattered cast iron fittings. It was just an annoying nuisance that engineers worked tirelessly to try and eliminate.
But Montgolfier looks at this destructive force and sees a feature. He realizes, wait, I can weaponize that violent pressure spike.
Yes.
I can trap that shockwave and turn it into an engine.
Which brings us to the actual execution of this idea. Because in 1796, Montgolfier builds the world's first self-acting hydraulic ram.
Okay, I really need you to break down the mechanics of this device for us, because reading about it, it honestly sounds like magic.
It does, doesn't it?
Yeah, like how do you turn a destructive shockwave into a perpetual loop that pumps water uphill without any external motor or power source?
Well, the elegance is entirely in its simplicity. So, picture a stream up in the hills.
Okay, I'm picturing it.
You lay down a long, rigid pipe, the drive pipe angling downhill toward the pump. Water enters this pipe and starts flowing downward, picking up speed and momentum just from gravity.
Right, basic gravity.
Right. And at the bottom of this pipe, inside the pump, the water escapes through an open valve, which is weighted so that it naturally wants to stay open. This is called the waste valve.
So the water's just rushing downhill and freely pouring out of this open valve at the bottom.
At first, yes. But as the water accelerates down the pipe, the velocity increases. And the drag of that rushing water, as it pulls at the open waste valve, gets stronger and stronger.
Okay.
To visualize this, imagine standing in a really fast-flowing river, holding an open umbrella pointing upstream.
Oh, wow. Okay.
Yeah, at a certain point, the force of the river is going to grab that umbrella and just violently rip it shut.
That paints a perfect picture. So the water's moving so fast, it physically snatches the valve and slams it shut.
Boom! That massive moving weight of water is brought to an instantaneous halt. That is the water hammer.
And there's the shockwave.
Exactly. The sudden shutdown creates an immense pressure spike. But this pump is a sealed environment, so that extreme shockwave has only one place it can go.
Where does it go?
It forces open a second, heavily sprung valve called the delivery valve.
Oh, so the shockwave essentially acts as like a liquid piston.
A piston made of pure kinetic energy. It blasts through that delivery valve and drives a portion of the water up into a delivery pipe, pushing it much, much higher than the original source it came from.
But wait, what resets the loop? Like, how does it keep going?
So once that shockwave passes and the energy kind of dissipates up the delivery pipe, the delivery valve immediately snaps shut under the weight of the water above it.
Okay, so the lifted water can't fall back down.
Right. And now the pressure in the main drive chamber instantly drops. And because that high pressure is gone, the weighted waste valve at the bottom naturally falls open again. Yeah, the water in the drive pipe starts flowing. It accelerates, the drag builds up, and it rips the valve shut once more.
Click, clack, the cycle just naturally restarts itself.
Over and over again. And depending on the setup, this happens anywhere between like 20 and 100 times a minute, endlessly.
Okay, I have to put on my strategic auditor hat for a second and push back here.
Let's hear it.
Because when anyone explains a machine that runs forever, powered by nothing, pushing heavy water uphill without a motor, my immediate thought is that we are breaking the fundamental laws of thermodynamics.
Ah, it sounds like it, right?
Yeah, it sounds like a perpetual motion machine and energy is never free.
Yeah.
Walk me through the system constraints. What is the actual input to output ratio here?
That is a vital distinction to make. This is not perpetual motion. It is entirely powered by the continuous, reliable force of gravity and the mass of the falling water. The energy is paid for by the water that falls away. The efficiency metrics of this system are staggering, though, once you look at the math. A properly installed hydraulic ram can lift water roughly 7 to 10 feet for every 1 foot of drop from the source.
Wait, so if I have a stream that drops just 8 feet down to where the pump is located?
That 8-foot fall generates enough shockwave energy to push water 80 feet uphill.
That is insane.
Even a modest stream with just a 6-foot drop can consistently deliver nearly 3,000 gallons of water a day up to a holding tank.
3,000 gallons. That is an incredible volume for something with zero electrical input. But there has to be a catch. The energy isn't free, like you said.
The trade-off is volume. The pump only delivers a small fraction of the water that flows through it, usually between, say, 10 and 30%.
Oh, I see. What happens to the rest?
The remaining 70 to 90% of the water is what actually powers the shockwave. Once that valve slams shut and the energy is transferred, the driving water just spills harmlessly out of the waste valve and continues down the natural stream bed.
Ah, okay. You're sacrificing a large volume of low-elevation water to achieve a high-pressure lift for a small volume.
Exactly.
So the system uses the mass of the 80% to launch the 20%.
Yes. But the true genius here is the continuity, because it requires no diesel, no electrical grid, no human intervention. It runs 24 hours a day, 7 days a week, 365 days a year.
Just endlessly thumping away.
Right. A slow, steady stream of lifted water accumulating around the clock yields a massive continuous supply over time.
That is the ultimate decentralized, fault-tolerant network. I mean, think about the deployment and scaling of a system like this in a pre-industrial world.
It was a game changer.
Yeah, this elegant open-source legacy code didn't just stay localized in Montgolfier's Valley in France. It went globally viral among the absolute greatest engineering minds of the era.
It really ushered in an open-source golden age for hydraulic technology. By 1798, the citizens of Portsmouth, New Hampshire, were actually gathering to watch a hydraulic ram run in their town's water system.
In America already.
Yeah. They dubbed it the Perpetual Pump, and it was reliably moving a barrel of water a minute, entirely on its own.
The heavy hitters of the Industrial Revolution were clearly taking rigorous notes. I mean, Robert Fulton, the visionary who invented the first commercially successful steamboat, he saw a ram pump running in Paris and began writing extensively about its potential.
Because steam power required massive supply chains of coal and wood.
Exactly. And this required absolutely nothing but a hillside. And then Matthew Boulton, who is James Watt's partner in commercializing the steam engine, he actually took out the British patent on Montgolfier's behalf.
Think about that. You have the greatest industrial mind of the age legally protecting the invention of a restless papermaker who built balloons.
It's incredible. And the implications for nation building were immense. Thomas Jefferson studied the mechanics, and he actively sought to acquire one for his Monticello estate by 1805.
Of course he did. He instantly recognized the strategic power of a water system that required absolutely nothing from a central authority. It meant pure independence.
Right. And by the late 1800s, you have this engineering firm run by a man named Josiah Easton, and they are mass-producing and deploying these heavy cast-iron pumps across the entire British Empire.
We have to talk about the Helligan estate in Cornwall, because the scale of their installation in 1880 is just mind-blowing.
Okay, set the scene for us.
The estate owners constructed this massive underground stone chamber. Inside, they installed 3 of Easton's ram pumps. Those 3 pumps worked in tandem, pushing water continuously uphill to a 40,000-gallon reservoir.
Wow.
And they did this for 80 years.
8 decades.
8 decades without stopping. No fuel supply chains breaking down. Yeah. No maintenance crews driving out in trucks every month to service a motor.
And it was just as vital for individual settlers as it was for these grand British estates. You know, in the American West, there's this pioneer named William Priestley standing on the edge of the brutal Snake River Canyon in Idaho.
Talk about a difficult environment.
Right. And he needed to irrigate his farmland, which sat 110 feet vertically above the river. He didn't have access to Josiah Easton's fancy engineering firm, so he just built a hydraulic ram out of basic boilerplate steel and standard pipe fittings.
That is true DIY survival.
Yeah. Powered solely by the falling springs along the canyon wall, his homemade pump pushed water straight up a sheer cliff to his crops. It was such an elegant, vital piece of survival engineering that the U.S. government eventually declared it a National Historic Landmark.
Which brings us to the million-dollar audit question of this digital stroll.
Let's hear it.
If this mechanical system was the absolute pinnacle of decentralized infrastructure, why was it deprecated? Why was such a robust piece of legacy code just deleted from the global operating system?
Well, it was the arrival of the centralized grid. Specifically, widespread rural electrification.
But it wasn't some dramatic corporate sabotage, though. The ram pump wasn't banned by some nefarious monopoly.
No, the reality is much quieter, which I think makes it far more insidious. It was replaced by pure convenience. Installing a hydraulic ram requires deep environmental awareness. You have to carefully calculate the natural drop of a stream. You have to measure the flow rate, lay a rigid drive pipe at a very specific angle to ensure the water hammer actually functions correctly.
It takes thought. It takes planning.
Yeah. But an electric pump, by contrast, requires no environmental harmony. You just drop a hose in the water, run a wire to a pole, plug it in, and turn a switch. So as rural electrification spread across America and Europe, a whole generation of mechanical wisdom was simply set aside.
There is a sharp observation in the source text that perfectly crystallizes this shift. It says gravity has never had a billing department.
Wow. Yeah, that is the crux of the deprecation, isn't it? We voluntarily replaced a perpetual independent solution with a massive dependency loop.
We really did.
Electric pumps depend on an active grid. The grid depends on centralized utility companies, vulnerable global supply chains, fluctuating fuel prices, monthly billing cycles, and we all know grids inevitably fail.
And this is exactly where Gurukul 2.0 philosophy provides such a vital lens for us.
How so?
Humanity has this tragic, systemic tendency to preserve only the knowledge that can be purchased, metered, and maintained by corporations. The knowledge that requires nothing but gravity, physics, and basic human ingenuity. That gets quietly deleted from our agricultural schools and our engineering curricula.
That's depressing, but true.
We remembered Montgolfier's balloon. We teach it in elementary schools. We name airports after his family because flight quickly became a massive monetizable industry. But the pump, the quiet click-clack that actually kept communities alive and hydrated on the ground, we collectively forgot.
We kept the sky, but we traded away the ground.
Exactly.
But the beautiful thing about legacy code is that it rarely dies completely. A durable architecture doesn't just vanish. Sometimes it just waits in the dark archives for someone to initiate a system reboot.
Yes.
And that brings us to the incredible restoration of the 1990s.
This is arguably one of the most poetic moments in the historical record of technology.
Tell us about it.
So in 1990, a record producer named Tim Smith was leading a project to clear out the wildly overgrown, abandoned gardens of that same Halligan estate in Cornwall we discussed earlier.
Oh, the one with the 40,000-gallon reservoir.
Precisely that one. The entire property had been reclaimed by nature after decades of neglect, and as his crew was excavating, 18 feet underground, behind a heavy door that had been completely sealed by a century of mud and roots, they discovered the original ram chamber.
No way.
Yes. Inside, covered in grime but structurally perfectly intact, were the 3 original Easton hydraulic ram pumps.
Over a century old, just buried in the mud.
Buried in the mud. The heavy brass valves were still perfectly seated. The cast iron air chambers were still holding their seals. Smith's crew carefully overhauled them, cleared the debris, renewed the inflow pipes, and in 1994, after 70 years of total silence, they opened the valves.
Oh, man, that gives me literal chills as an auditor.
The water rushed down the drive pipe. The drag grabbed the waste valve. Click, clack. The shock wave returned. After 7 decades buried in the earth, they immediately began pushing water back up to the reservoir, 24 hours a day, without drawing a single kilowatt of grid power.
That is the ultimate proof of concept for the Project Antaryami framework. I mean, a system so robust it can sleep for 70 years and wake up working perfectly.
Beautiful.
And for anyone walking with us today, here is the immediate practical application of all this. You don't have to fly to Cornwall and dig 18 feet into the mud to harness this.
Definitely not.
You can build a modern iteration of this legacy code this weekend for under $200. Agricultural extension offices at universities like Clemson and NC State actually have completely documented open source DIY plans available for anyone.
And the materials are remarkably accessible at any local hardware store.
Right, like what do you actually need?
You need a long piece of rigid drive pipe, typically galvanized steel so it doesn't flex under the pressure spike. You need a heavy brass waste valve that swings on a hinge and a standard one-way delivery check valve.
Okay. Pretty standard plumbing stuff.
Yeah, and the pressure vessel itself can actually be constructed from thick-walled PVC pipe. But there is a brilliant modern adaptation the universities recommend for that.
What's that?
Placing a simple inflated bicycle inner tube inside the PVC pressure chamber.
Wait, a bicycle inner tube. How does that factor into a high-pressure water system?
Well, the water hammer generates incredibly violent spikes of pressure. In the old days, the cast iron could handle the shock. But modern PVC could eventually shatter under that repeated stress.
Ah, okay.
So the air inside the bicycle inner tube acts as an accumulator, a highly compressible shock absorber. When the shock wave hits the chamber, the inner tube compresses, absorbing the violent spike and turning it into a smooth, steady push up the delivery pipe.
That is a phenomenal hack.
Isn't it?
And the environmental requirements are incredibly low. You only need a water source flowing at a minimum of 2 to 3 gallons a minute and a mere 3-foot drop in elevation to get the whole system thumping.
That's really all it takes.
Plus, because this operates entirely off-grid and you are simply managing surface water mechanically on your own land, in most jurisdictions, you don't even need to pull a municipal permit.
Which is huge.
As an auditor, I look at the vulnerability of our modern infrastructure. The rolling blackouts, the strained electrical grids, the fact that diesel backup generators inevitably run dry during a prolonged crisis. Is the ram pump the ultimate fail-safe for modern homesteads?
I mean, it is the purest physical definition of resilience. When the grid drops, the stream keeps flowing. Gravity doesn't experience power outages.
No, it doesn't.
Somewhere in a forgotten, overgrown valley right now, an iron hydraulic ram pump from the 1800s is still thumping away. Click, click, clack. It is just waiting out there for anyone willing to clear the brush, look at the water differently, and, just listen.
As we synthesize what we've uncovered through the digital prism today, we really have to look at the legacy of Joseph Montgolfier. In a span of just 13 years, he handed humanity 2 massive gifts.
Yeah.
He gave us the balloon, which proved that human ingenuity could defy gravity and carry us into the clouds. And he gave us the perpetual pump, which harnessed that exact same gravity to keep us sustained and alive on the ground.
2 completely opposite applications of energy.
Over the centuries, we eagerly embraced the centralized grids, the utility companies, and the fragile dependency loops. But the legacy code of true decentralized resilience is still out there, completely unmetered, running endlessly on pure physics.
And I want to leave everyone walking with us today with a final Guru Cool session thought to ponder on your own time.
Lay it on us.
We just explored how a society systematically forgot a life-saving perpetual technology simply because it couldn't be metered, monetized, and billed on a monthly cycle. If we let the hydraulic ram fade into the mud, what other miraculous, self-sustaining legacy codes are currently buried under the weight of our modern conveniences? What other perfect analog solutions are just waiting for you to clear the dirt, open the valve, and listen for the click-clack?
What a profound question to walk away with. Thank you for joining us on this continuous journey into the Project Antaryami framework. Keep walking, keep questioning the systems around you, and we'll see you on the next Digital Stroll.